Hi everyone, my name is Daniil and I'm going to present our work with Mika and Bas on code extraction from Coq to ML-like languages. Before I start explaining our approach, I would like to say what code extraction is. Proof assistants feature expressive languages often based on dependent types, which allow to write specifications of programs directly in types. That facilitates correct by construction programming, which is important in new domains such as smart contracts and web programming. And we would like to leverage the power of dependent type in these domains. But implementing a dependent type programming language is hard. Maybe we can somehow use existing proof assistants which already feature dependently typed languages. But how can we obtain a program from the formal development? This is precisely what code extraction is all about. It's about producing executable code in a conventional programming language. And such functionality is available in many proof assistants such as Coq, Agda, Isabelle, and so on. And a common extraction target are functional programming languages. Specifically, we will focus on the Coq proof assistant. And for this proof assistant, one have a support for extraction to OCaml, Haskell, and Scheme. And general idea of this extraction procedure is to find and identify computationally relevant bits and turn them into a box, which could be further eliminated by optimizations. Therefore, proofs and types appearing in terms become boxes and further they get eliminated. And the underlying theory of for such a transformation is developed by Pierre Letouzy in his PhD thesis. But unfortunately, this is not sufficient for what we have in mind. In particular, we would like to target new languages, such as, for example, languages for smart contracts. And moreover, current Coq implementation of extraction itself is not verified. But there is a very nice project called MetaCoq that adds metaprogramming facilities to Coq and also formalizes large portions of Coq's meta theory. Moreover, it features a verified erasure procedure, which is a crucial ingredient to extraction, and that's what we're going to use to build our pipeline. Here is our pipeline, and let me guide you through it. Our development is inspired by the use case of smart contracts, and we're going to talk about this use case later in the talk. And it's done as a part of the Consort smart contract verification framework. For now, we can think of smart contracts just as ordinary programs in Coq. So, green items on this slide correspond to our contributions, and items marked with a star correspond to verified procedures. So we start by developing a program in Coq from which we can obtain a template Coq representation using quote facilities provided by MetaCoq project. Essentially, it allows us to get an abstract syntax for the original program. On this abstract syntax, we define various transformations along with the procedure that generates proofs that the transformed terms are equivalent to the original ones. From the template Coq representation, we obtain a representation in core calculus of Coq called Pickwick, which is essentially a version of calculus of inductive constructions. And precisely for this representation, MetaCoq features various meta-theoretical theorems. From Pickwick representation, we obtain a so-called lambda box T representation using the verified erasure procedure of MetaCoq, and also our procedure for extracting types, which as a result gives us a calculus of array programs extended with typing information, which we use as an intermediate representation. On this intermediate representation, we perform optimizations. In particular, we remove unused arguments of constants and constructors. From the intermediate representation, we can produce code in concrete syntax for several target languages. And currently we support 2 languages for smart contracts and 2 general purpose languages. And today we're going to focus on Camel Legal and Liquidity, which are Camel-inspired languages for smart contracts, and the Elm language for web programming. We also integrate our development, our optimization path with CertiCoq, which is a certified compiler for Coq. The trusted code base includes the usual of Coq, plus quoting facilities of MetaCoq, and pretty printing and the runtime of target languages. As I mentioned before, smart contracts were one of the motivations for the development, and let me briefly introduce what they are and give some examples how we use our extraction pipeline for smart contracts. The smart contract technology is tightly related to blockchains, and you can think of a smart contract as a program deployed on a blockchain, and a blockchain in this case can be seen as a replicated database, and smart contracts are particular kind of stored procedures for this database. And what is so special about these smart contracts? They are designed to manage money and various assets. Therefore, typical applications include auctions, crowdfunding, multi-signature wallets, and so on. And after deployment, the contracts are immutable, meaning you cannot modify the code. And the execution of a contract is reversible, meaning that the transaction you cannot roll back a transaction even though it might contain some mistakes. And it's exemplified by several examples that even small flaws might lead to huge financial losses. And the recent attack to Poly network resulted in $600 million stolen. Many modern blockchains employ the functional programming paradigm for smart contract languages. In particular, in this case, contracts or smart contracts become partial state transition systems that take some information about who calls the contract, user-defined type of messages, user-defined state, and return new state, and the list of actions. All probably fail, so that's why it's wrapped an option. And there is a special piece of software that is responsible for executing these actions in this list. And these actions could be transfers from one account to another or calls to other contracts. In this work, we consider 2 Camel-inspired languages for smart contracts, namely Camel Legal for Tezos network and Liquidity for G network. Since we considered new target languages which are different from the conventional targets such as Ocama and Haskell, we also discovered several new challenges. In particular, it's well known that the type system of Coq is very expressive. That means that extracted programs sometimes cannot be type checked in the target language type system. Therefore, it solves in standard extraction by inserting unsafe type coercions, but they're just called unsafe, right? Because potentially it can lead to some issues. But given that we have a guarantee that dynamic semantics of our terms is preserved, inserting such coercions is usually safe. But unfortunately, such coercions are not available in our target languages. Moreover, there are certain restrictions from the languages regarding data types. For example, both in Camel Legal and Liquidity, only non-recursive data types are supported, and collections such as lists, for example, are given as primitives. Also, in Camel Legal, it's not possible to define polymorphic types in functions. Only, again, the ones that are provided as primitives are polymorphic. And the recursive definitions are limited, the recursive functions are limited only to tail recursive definitions. It has the following consequences. Some extracted code won't be well typed, and we have no opportunity to force the type checker to succeed due to the absence of mechanisms such as automagic or unsafe curves. Currently we do not support non-tail recursive functions. Moreover, since many definitions which we use in Coq, such as lists, for example, cannot be expressed directly in the target language, we need to apply so-called remapping, which basically means we say that list in Coq corresponds directly to primitive list in common legal liquidity. And the same happens with the functions defined on these lists. And basically that the same applies to all collections and also to arithmetic operations. And so how do we address these challenges? First of all, we provide a certifying pre-processing step that performs some transformations such as inlining specialization and generates proofs that the transformations don't break semantics of the term. And precisely these transformations can be used in many cases to produce code that actually type checks. Moreover, we allow for configuring a translation table that precisely designed to solve this remapping problem, saying that certain Coq data types correspond to primitive types in the targets. Before I talk about examples, I will briefly introduce a particular kind of dependent type that we will use for developing a smart contracts and our web application. So it's called subset types, and essentially these are types with a predicate. You can think of it as a Coq version of refinement types. In Coq itself, it's defined as an inductive family with one constructor. Inductive family called sig, and a constructor called exist. And the constructor takes a value and a proof that some predicate holds for this value. So you can think of inhabitants of this type as a value proof pairs with two projections. First projection can be used to get value out of it, and second projection to get the proof. We use curly braces notation for our sig type or for a subset type, and here's just some examples how it can be used. For example, we can encode a type of strictly positive numbers using this definition, or type of non-empty lists. Moreover, Coq provides program environment for managing proof obligations, and that helps to work with subset types and makes writing programs in Coq using subset types convenient. Moreover, it's convenient for extraction as well, because the second component is a proof, and proofs are erased by the extraction procedure. So let us consider a simple smart contract, which we will counter, and as I said, it's just an ordinary function in Coq, and in this case, this function takes a user-defined message type, which is increment or decrement, and a storage or the state of a contract is just modeled as an integer number. And the goal of this contract is to react on increment and decrement messages and update return new storage. So to implement the main functionality, we implement two functions, incCounter and decCounter. Let us consider how incCounter function works. So we use subset types to encode invariants. In this particular case, we say only positive increments are accepted. Moreover, the return type is also a subset type that ensures that new storage, the updated storage, is indeed greater than the old storage. And we can use, again, we use program environment here, and we can use inc parameter as it was just a value, and program environment will insert constructors of the subset type and projections if necessary. It also will show us proof obligations in case it cannot prove them automatically. That can be resolved using tactics. In order to call inc counter function from the entry point, which is our counter function, we need to perform data validation. That's what we do here, and then after validation we use the results to construct the proof. In this case, the proofs would be necessary in order to call inc counter function. Here's the result of extracting this counter contract to liquidity. And the signature on the contract, the entry point, extracts with no surprises. Basically, type of messages becomes a variant type with two constructors, and storage becomes an alias now to an integer type of integers. The interesting thing happens here, so the logical bits corresponding to proofs are erased, and the signature, the sig type becomes just a wrapper around the value. Let us jump to a next use case, specifically extraction to Elm and example web application. So Elm is a general purpose functional language that is mostly used for web programming. It is based on Hindenburg type system, and it's actually a very nice extraction target because many features that are usually found in functional languages are present in Elm. And our intermediate representation, lambda box t, is very close to the constructs available in Elm. But it still lacks ability to convince a type checker that a code is safe. So for us, we were able to identify that if one writes programs in premix polymorphic fragment with subset types, that it leads to well-typed Elm code. But we can actually go further if we use our pre-processing step in the pipeline to inline the specialized definitions. Then we can handle higher kinded types. For example, we can use monads, and then after unfolding, it will still result in well-typed Elm code. So let us consider an example web application which is inspired by the Elm guide, and so it can be found also online. Basically, it's an input form with the user and password, and it stores list of users after performing some validation. It stores the list of users on the client side. So we define the logic of the app in Coq and use dependent types to encode some model invariants. That's how the model for our web application is defined. First of all, we define type of stored entries, which consist of a name and a password, and afterwards we define what does it mean for the entry to be valid. And valid entry is an entry with a non-empty username and a password which is longer than 8 characters. Then the model is a list of users such that each user is represented by valid entry. Moreover, this list does not allow duplication of usernames. The model also contains a list of errors that we populate after performing the validation step, and it contains a current entry. So the entry type is not given here, but you can imagine it as is raw user input, which we have not validated yet. User valid entries has an advantage that whenever you write a function on these entries, you know that you will have to preserve the model invariants, so you never break the validity of them. And since you always work with entries which already carry proof of validity, you don't need to for extra validation in any other part of your web application. Moreover, at the entry point, since you need to, in order to populate data to the model, you need to construct a valid entry. At the entry point, it forces you to construct the proofs, meaning it forces you to think about validation and basically follow the constraints that you specified in types for a model. And the nice thing about this user list, basically, if you go back to the previous slide, so the users are list of valid entries with no duplication. That basically forces us to store only valid entries as a state of our application. So in the course of the development, we use again program environment for convenient programming with subset types, and we also use monads, and after unfolding the definitions, it results in well-typed Elm code. Therefore, we verify application logic, extract code, then append the views. And the views, it's basically the code that is responsible for rendering HTML, and it contains calls to the entry point of our model. The example is available in Ellie, which is an online IDE for Elm, and you can find the link in the abstract. There are possibilities for interesting extensions to this work, and thanks to the reviewers for asking these questions. We actually can go a little bit beyond verifying just a model. We would be interesting to verify how the interaction part works. Basically, so the views, they call methods, updates methods of our model, and we can model this. We can create a model of Elm runtime in Cog and verify properties of interaction between the view and model. And this model is actually quite similar to something we already developed for smart contracts as part of the Consort framework. And I think with maybe some tweaks, it would be possible to adapt it to web application verification for Elm. And to conclude, we presented a pipeline for extracting programs from Cog to functional programming languages. And the pipeline is implemented completely in Cog, allowing for verification of various parts of the pipeline. And currently, the most crucial parts of the pipeline are verified. Moreover, the pipeline offers the possibility of extending the pre- and post-processing steps with new user-defined transformations. We also showed examples of applications of the pipeline to smart contracts and web programming. The main takeaway of this talk is that one can use the Cog proof assistant and our extraction to bring the power of dependent types to your favorite functional language. So basically it just boils down to adding a pretty printer to your language at the very end of our pipeline. Thank you for your attention, and our development is available open source on GitHub as a part of the Consort framework, and please go ahead and add new target languages. And I'll be happy to answer your questions.